Hello everybody, this is a video going over the solutions for the, sorry about that, for the homework for the repeated measures ANOVA. And so the first problem is this. We're looking at full moon, new moon, and half moon. So measured hospital admissions, which is the DV for these 7 hospitals. And so just like with any ANOVA problem, the first good step is to make the worksheet. So here's the worksheet. So I've taken the raw data from here and I've done the worksheet. And so again, this part of the worksheet is the same as what we did for the one-way ANOVA. So you're probably pretty familiar with this. And so, the first step I basically do is I set up a column where I'm squaring each of the scores. So 6 squared is 36, 7 squared is 49, etc. Want to do the same for new moon. 8 times 8 is 64, 17 times 17 is 289, and then for the half moon. So 5 times 5 is 25, 12 times 12, 144, etc. So I set up those, and then I want to add, so I end up adding all these columns. So I add the squares, so this is the sum of squares for full moon. So the sum of the squares is 399. So here's a sum of squares, 399. So then we have the squares for new moon. The sum of the squares for new moon is 871. And then half moon, so we have all these squares, add them together. The sum of the squares for half moon is that, 431. And then I go ahead and then add the raw scores. So the raw scores, and then this is T. So the T for FM is 49. If I take 49 times 49, I get T squared. Same thing for new moon. Oops, sorry about that. Add the scores together for the 7 hospitals. This is our T. Then T squared is 73 times 73. This is T squared. And then half moon. We add the scores together. This is our T. T squared is 53 times 53. So 2,809. So I have my T right here. I can find the mean. So I take T divided by 7. There's 7 hospitals. 49 divided by 7. There's an average of 7 for full moon. I have my T here. 7 divided by 73 is 10.43 is the mean for new moon. I have my T here for half moon. So I take that T and I divide it by 7 to get the mean of 7.57 for the half moon. And then I can take the raw scores for each of the 3 moon conditions, and I can find the standard, the sum of squares and the standard deviation with the online calculator. Same thing here. Use these scores for new moon. I can find the sum of squares and standard deviation for new moon with the online calculator, and then I can put these scores in for half moon, and using the online calculator, find the sum of squares and standard deviation. So those steps are exactly the same as what we had for the one-way ANOVA, so you're probably pretty familiar with those. And then we have the P that we need to do for repeated measures. So remember, P is adding up the scores for, we say person, but in this case it's the hospital. So it's whatever participant it is. In this case, it's hospital. So we do full moon plus new moon plus half moon, 6 plus 8 plus 7. The P is 21. And then P squared is 21 times 21 is 441. For hospital number 5, we take 3 plus 8 plus 7, and that is 18. That's the P for hospital number 5. We take 18 times 18 to get 324. So basically, we just have to go through the steps of finding P and then P squared. So once we've done that for the 7 hospitals, now we end up with all the stuff that we need. So again, the key to solving these ANOVA problems is that there's just a little bit of steps. But once we do things like this with the worksheet, then we just go through step by step with the sum of squares, degrees of freedom, mean squares, and then we have our F. And so let me go through this. So I've actually already did G here. So the G is just taking the T's. So the T's were 49, 73, 53, right here. I added the T's together to get the G. And once I have 175 for the G, I take 175 times 175 to get G squared, 3,625. So now it's just plug-in time. So here, we're going to do sum of squares total. So the first part is the sum of x squared. So remember that we took the squares of each of the scores and we added them together. So remember we had the squared scores for FM, squared score for new moon, squared scores for half moon, and then we added them up. So the sum for FM was 399. The sum for new moon was 871, and the sum for half moon was 431. And so we just add those together to get the sum of x squared. 399 plus 871 plus 431. So we just add those together. And then we have to take g squared, which we found up here already to be 30,625, divided by capital N. Capital N, we have 7 hospitals. They were measured 3 times, so 7 times 3 is 21. So now we just solve. We add these together. We get 1,701. We take g squared divided by capital N, so we take 30,625 divided by 21. We get this number. So then we take this minus this. So 242.67 is the sum of squares total. And again, this is the same approach that you would take for one-way ANOVAs, but also obviously for the repeated measures. It's the same step. The same step also is for within. Actually, I do between first. So sum of squares between. So for every condition, the new moon, half moon, full moon, we have to find the t squared, which we have in our worksheet, divided by small n. Small n is the number of measurements within the condition. So there's 7 hospitals. So small n is always going to be 7 in this case, 7 hospitals. And then we take that minus g squared over capital N, which we already know is this, because we figured that out in the sum of squares total, right here. Sum of squares total, we already figured that out. We already figured out this ratio equals this. So you can just go ahead and put the g squared over n as that in this part of the problem. So that is already solved in the sum of squares total. So now we just have to take the ratios of t squared over n for each of the conditions, new moon, half moon, full moon. And so we go up here and we add the sum, we add together those ratios, the t squared over n. So remember we have t squared here. I want to show you the full worksheet. So remember we figured out t squared right here, which was the t and then square it. T, the sum of the raw scores, square it. T, sum of the raw scores, and squared it. So t squares are here. So 2,401, 5,329, and 2,809. And voila, here they are. And remember that for each of those t squares, we have to divide it by n, small n, which is 7. We have 7 hospitals. So we have this ratio for, I think it was, I want to find out the full moon, new moon, half moon. So that's the ratio for full moon. That's the ratio for, I just looked at the stupid thing, new moon. And then this is the ratio for half moon. So we solve for these ratios first. So solving for the ratios, we get these numbers. And then we have to add these numbers together and then subtract 1,458.33, which is what we found to be g squared over capital N in the SS total. So we go ahead and solve that. And SS between treatments is 47.25. Okay, so let's go ahead and go back here and we'll look at the I'm sorry about this, at the sum of squares within each treatment. Sorry about this, I'm skipping around a little bit. I was actually thinking something about the course that I want to do, and that's interfering a little bit with my process here. So let's do the SS within. So the SS within is just adding up the sum of squares for each of the treatments, each of the moon phases in this study. So we just found that with the online calculators, and we have it in our worksheet. So we have the sum of squares here. We have 56, 109.71, 29.71. We just add those together. That's our sum of squares within, right there. So our sum of squares within is 195.42. And those steps, again, are exactly the same as what we had to do for the one-way ANOVAs. But now we have to do the new things. The new things is that we have to reduce the within subjects variation by taking the sum of squares between subjects to find the error. So here's the new stuff. I don't know if I can highlight it or not. It's not highlighting it, just boxing it. So remember, we have to find those individual differences. So hospitals, in this case, they might be in different neighborhoods, and they may lead to more admissions depending on what type of neighborhood it is. And so we want to get those individual differences. If are some hospitals just generally higher? Who cares about moon phase? Just are some hospitals generally higher than other hospitals in terms of emissions, regardless of the moon condition? So in this case, we have 7. And by the way, here's the same thing. G squared over capital N, which we already know is 1,458.33. We figured that out way back in the sum of squares total, so we can just bring it down here. So now we have to take each hospital and figure out the p squared over k. So just to remind you, we have all of this information in our little worksheet. So we have p squared for each of the 7 hospitals. And then we have to divide the p squared by k for each of the hospitals. And k is the number of conditions. We have 3 moon conditions: full moon, half moon, and new moon. So we just take the p squared, divide it by 3 for each of the hospitals. And so this is what we're doing here. And so this is this part of the formula. So each of the 7 hospitals, so you'll see that there's 7 ratios here. We'll take their p squared and divide it by k. K is 3 in this case. So we have all these ratios. We have to solve for these ratios first before we do anything else. So for each of the 7 ratios, go ahead and solve that. And then add these together in this parentheses. And then subtract that g squared over capital N, which we already know is 1,458.33. You're going to end up with 163.33, give or take some rounding here and there. So that's our between subjects. So that's now an index of how much do the hospitals just general and vary, knowing that some hospitals may have more admissions than others. So this is what we're indexing here. We're measuring that here. So now we have our old sum of squares within treatments. We already figured that out, and then we figured out the new sum of squares between subjects. Now we can figure out our error, which is the within minus the between subjects. So we just plug in the numbers here. And so the sum of squares error now is 32.09. So we did all of our sum of squares. Whoops. Now we can get to the degrees of freedom. Degrees of freedom total is just the same approach as what we've been doing all along, including the one-way ANOVA. basically, how many numbers do we have in terms of measuring the DV? Well, we have 7 hospitals measured 3 times, 3 moon phases. So 7 times 3 is 21. So capital N is 21 minus 1 degrees of freedom. So then you have 20 for your total degrees of freedom. And then the degrees of freedom within treatments. And again, treatments here are the different moon phases, the 3 moon phases. So we know we have 7 hospitals. I don't know if you can see this here. I'll make it a little bit bigger. So we have 7 hospitals. And so in each moon condition, we measured 7 hospitals. So degrees of freedom in each of the moon phases is 7 minus 1. So it's 6. For every single one, we have 7 hospitals. So 7 minus 1, 6 plus 6 plus 6. We have 3 conditions. 6 plus 6 plus 6 is 18. Or you can just take it 6 degrees of freedom times 3 condition is 18. Same thing. The degrees of freedom between treatments is exactly the same as what we were doing for the one-way ANOVA. So we had 3K, so we have 3 moon phases, 3 levels here. So it's 3 minus 1 is 2. And remember I said in the video before is that somebody asked me this question, they were confused, why is this always 2? It's always going to be 2 because I'm only going to give you 3 levels. I'm not going to make you do more than 3 levels because that's extra work. So why do extra work when you're learning the same thing anyways? Then our degrees of freedom between subjects is small n minus 1. Remember, small n is how many things do you have? Well, we have 7 hospitals. So small n is 7 minus 1. So 6 degrees of freedom for between subjects. And then error, degrees of freedom error is always going to be within treatments minus between subjects. So in this case, degrees of freedom within minus degrees of freedom between subjects. So up here, we found within was 18. Between subjects was 6. So 18 minus 6, we have 12. You can also take this approach, k minus 1 times n minus 1. Well, k is 3. We have 3 moon phases. And small n is 7. We have 7 hospitals. So k minus 1 is 3 minus 1 is 2. And then n minus 1 is 7 minus 1, that's 6. So 2 times 6 is 12. So either approach is going to give you the same number. You only need to take one approach unless you want to do some sort of double check of what's going on. So now we have our degrees of freedom. And so remember, for the F for the repeated measures ANOVA is that we're going to take the old way of doing the MS between treatments. That's the same. So we're going to find out the MS between treatments with the sum of squares, degrees of freedom. But in this case, we're going to be using that smaller error. On the bottom of the F is the error, so we'll get the MS error, which is the sum of squares divided by degrees of freedom for error. Oops. So let's go down and do that. Oops. Let me go back to my key where everything is. So like I said, the top is the same. We need to get the MS between treatments, just like the one-way ANOVA. And so we just plug in the sum of squares between treatments divided by degrees of freedom between treatments. So our mean squares between treatments is 23.63. And then we need to figure out the mean square error that goes on the bottom of the F. So anytime you're doing the mean squares as an average, so the average is the sum of squares divided by degrees of freedom. So sum of squares error divided by degrees of freedom error, our mean square error is 2.67. So then our F is the MS between treatments divided by the MS error. So we just plug in our numbers that we found above. So 23.63 divided by 2.67, we get 8.85 as our F. We go find the critical value for the F with 2 degrees of freedom for the between treatments, that's the columns, and 12 degrees of freedom for error, which is the rows. And we go ahead and find that in the table, and we get 3.89. So our F that we calculated, 8.85, is greater than 3.89, so we reject the HO. So there is some sort of difference in hospital admissions based on the moon cycle. We don't know what those differences are. We just know there's some difference. So we will have to do a little eyeball scanning because we aren't going to hand calculate post-hocs. And then we have the one last calculation, which is to figure out the effect size. Again, you can use either of the two formula. I'm sort of promoting this one because it's a bit easier because we have the same number that we repeat twice, so it's a little bit quicker to do. So, but if you do the other formula, the final answer should be the same thing. So sum of squares between treatments divided by sum of squares between treatments plus sum of squares error. So we just plug in the numbers from above. We've already calculated this stuff. So make sure on the bottom you add these things first and get 79.34. So you divide this and you end up with 0.60. So essentially 60% of the hospital admission seems to be directly related to the moon phase, which is a large effect. So I have already put the tables here. So don't forget to get the descriptive tables of the mean and standard deviations. And again, we're going to be comparing the means of these conditions. And since I'm here, I'm going to look at these already. So we aren't doing formal post hocs, but we're going to do an eyeball look. And eyeball looks like new moon is higher than half moon and full moon. And it looks like it's substantially higher, roughly a standard deviation higher. Okay, let me go ahead and go down a bit. And then we want to do a ANOVA summary table. And we're just plugging in the numbers from our calculations above. Remember, for us, we're not going to put in the total row because I don't want you putting in the total because I don't want you thinking that these numbers have to add up. They don't. Total is actually here. So if you added these things together, you would get the sum of squares total and degrees of freedom total. But let's not bother with that because what we really want is we're really focusing on this and we're focusing on the error. But I want you to see the process because the process is to find the error, we take the within treatment stuff, divide it by between subjects, or not divide it by, subtract the between subjects, and we get the error. So sum of squares, we take the within, the old within, we subtract the between, and we get the error. And then for degrees of freedom, same thing. We take the old within, subtract the between to get the error. So once we have that, we need to get our mean squares again, between treatments. Sum of squares divided by degrees of freedom equals mean square. Sum of squares divided by degrees of freedom equals mean square. Mean square between treatments divided by mean square error, we get our F. And remember that we rejected the HO at the 0.05 level, and so we put a little star there. And so our write-up is exactly like what we've been doing all throughout this ANOVA process. So we have a sentence or a phrase that we refer to table 1 for the descriptive statistics. We have table 2 for the ANOVA table, summary table. And then we, in a sentence, we simply say the relationship between the two variables. So moon phase, our predictor variable, was significantly related to psychiatric hospital admissions, which was our DV. So this is just a simple statement of a relationship. Is there a relationship or is there not a relationship? Remember, the ANOVA does not tell us direction, which direction this goes. It just tells us there's some relationship. And then we give the stat information. So the F, and then we have the degrees of freedom between treatments is 2. Degrees of freedom error is 12. Our 8.85 is the F that we calculated. And then we found that we rejected the HO at the 0.05 level. So P is less than 0.05. So the probability of a type 1 error is less than 5%. And then I threw in the effect size here. I noticed that I threw the effect size in here. And in the lectures, I had the effect size as the last sentence. It doesn't matter. Either way is fine. And then we want to be honest with people. Scientists should be honest, and statisticians should be honest. We didn't do postdocs. However, if we looked at that table number 1, we noticed that new moon was higher on emissions versus half moon and full moon, and those two, half moon and full moon, did not seem to differ. So that's the solution for problem number 1. Let's go to problem number 2, and I'm going to show you the raw data. So here we have different conditions, and we have people use different memorization techniques, repetition, chunking, or rhyme. And then we measure people on a test to see how well they remember using those different methods. And it's within subjects, so each person gets a chance to use each of the methods, and we test that method. So there's 3 measures of the DV for each person, and it looks like we have 6 people in this study. So 6 times 3, we have 18 measures of the DV. So our first step, as usual, is to do the worksheet. And again, this part of the worksheet is exactly the same as what we had done for the one-way ANOVAs. And so typically how I do it, and I don't know, maybe I'll just say it different this time because I'll just shake it up because people might do it differently. You could just simply add the raw scores for each of the conditions. So here, repetition, add them together. This is our T. 64 is T for repetition. And we want T squared, so we take 64 times 64 and we get T squared right there. We do the same thing for chunking. So go ahead and add the raw scores for chunking. Add them together. 73 is the T for chunking. To get T squared for chunking, we need 73 times 73, so we get 5,329. We do the same thing for rhyme. Add the raw scores together. This is our T. We take 87 times 87 to get T squared for rhyme. We also want to square the raw scores. So for each raw score, we square it, and we make a new column right here. So we make a column. So 10 times 10 is 100. 9 times 9 is 81. Again, we do that for all the raw scores. So then we go to chunking. 15 times 15 is 225. 13 times 13 is 169. So we do it for repetition, chunking, and rhyme. We square the raw scores, and we have these columns. So we can simply add these columns, or I'm sorry, these scores together, and then we'll get the sum of x squared for repetition here. We'll take these scores and we'll add them together and we'll get the sum of x squared for chunking. And then we'll take these scores, we'll add them together and we'll get the sum of x squared for rhyme. And then the only other steps we need to do that is sort of the old steps is we need to find the mean. So you take the t, divide it by 6, you get these means. And then the sum of squares and standard deviation is you put those raw scores in from the column for each of the columns. And from the analog calculator, you find the sum of squares and the standard deviation. The new stuff is the p and p squared. So we have to do this 6 times. There's 6 people. So we want to add repetition, chunking, plus rhyme. And so for person number 1, 10 plus 12 plus 15 is 37. That's their p. And then we need to figure out p squared. So it's 37 times 37. That's 1,369. So we do this for everybody. For example, person 5. 11 plus 15 plus 18 is 44. 44 times 44 is 1,936. So we're going to figure out that P, and again, the P is to see if people are higher or lower. And it looks like we have some people who are a little bit high, so Person 5 and 6 looks like they're high, just in general. You know, regardless of the technique, they seem to be higher than other people. And I'm getting this just from looking at the P. And then it looks like person 4 is just lower. It looks like they have the lowest score on each of the conditions, so they're relatively lower. So P again is an indicator of individual differences on the DV. Are there people higher? It looks like 5 and 6 are higher, and 4 is lower. And the other people might be somewhat around the middle. So now we have our worksheet, and then it's simply filling in the blanks. So I do G square first here. So I'm going to take the T for each of the groups. So remember, each of the groups we added their scores together. Got a T here, 64. T here, 673. T here, 87. We just add those together to get the G. Add the three T's together, get the G. G is 224. And then 224 times 224 is 50,176. Now we're ready to roll. Now we can do sum of squares total, which is the sum of x squared minus g squared over n. So remember, sum of x squared is up here. We did that already in terms of each of the groups. So we have r squared here. We have repetition squared. We have chunking squared here. And we have rhyme squared here. And so we added those together. So sum of x squared for repetition is 704. Sum of x squared for chunking is 911. And sum of x squared for rhyme is 1,303. So we have all that stuff. So we just put all of the x squares here, the sum of x squares for each of the three groups. And then we have to get g squared over capital N. So remember, g squared was 50,176. So g squared divided by n. Remember, we have 6 people measured 3 times, so we have 18 scores. So capital N is 18. So we add these three numbers together, sum of x squared. We get 2,918. And then we take the ratio, g squared divided by capital N, and we get 2,787.56. So our sum of squares total is 130.44. And we go to the next step. The next step is the sum of squares between treatments. So our sum of squares between treatments is just like the one-way ANOVA. We are going to take the t squared divided by small n. Small n in this case is 6. We have 6 people in our study. We're going to do that, and then we're going to subtract g squared divided by n, which we already know is this. We already figured that out in the sum of squares total above, so we can just put it down here. So now we have to get the t squared divided by n, small n. So remember that we have t squared here. For each of the three conditions, we have t squared there. So we just bring these three things down. And for each of those, we have to divide it by small n. Small n is 6 people. We have 6 people in our study. So we take each of the t squares, divide it by 6. Next t squared divided by 6. Next t squared divided by 6. We solve for these ratios. Right here, we have to add these things together, these three things together, and then we subtract the g squared over n, capital N. And then our sum of squares between treatments is 44.78. And then the final thing that's similar to the one-way ANOVA is the sum of squares within treatments, which is just adding the sum of squares in each of the treatment groups. In this case, the treatment groups are the repetition, chunking, and rhyme, whichever strategy that we had them use. So you put those raw scores into the online calculator and you found the sum of squares right here. So you just add those three numbers to get the sum of squares within. Add those three numbers, you get the sum of squares within. And so the next thing we have to do, so we have the sum of squares within, but we have a repeated measures ANOVA, so we have to find out this new thing, This new thing being the between subjects. So we already know that there's a couple people, 5 and 6, in our study that look like they're pretty good in general. They get high scores in general. And there was a person who got low scores in general. So this is going to tell us how big are those individual differences, and we have to subtract these things from the old within to find the new error term. So this thing's the same. G squared over capital N, we already know it's 2,787.456. I'm sorry. We figured that out already in the sum of squares total and also between the sum of squares between treatments. We can just bring down that number. We don't have to recalculate that. And all we have to do is find p squared for every person and divide it by k. K is 3. And so we just simply go to our table. And so we take the p squared for each of the 6 people, divide it by 3, that's the number of conditions, k, and we just plug it in. So, and we're going to do this 6 times. We have 6 people, so we have this ratio for 6 people. P squared divided by k, which is 3, p squared divided by k, which is 3, p squared divided by 3 for these 6 people. We solve for these ratios right here. We add these things together, we add these things together in the parentheses. And once we've done that, we subtract that total from 2787.56, which is the thing that we've had all along for G squared over capital N. We've gotten that ever since the sum of squares total. And we come up with 69.09 for sum of squares between subjects. So that's our measure of individual differences. Are there people who are higher, lower, in the middle, regardless of the technique that they're using to memorize? So now we have our new between subjects, and now we can find out the error. Error is always going to be taking the old within and subtract the new between subjects, individual differences. So in this case, it's the sum of squares within minus the sum of squares between subjects. We just simply plug it in. And our sum of squares error is 16.57. So we have all of our sum of squares, and now we have to get the degrees of freedom. So the degrees of freedom total is the same as what we were doing for the one-way. How many scores on the DV do we have? -1. So we have 6 people. We've measured them 3 times. There's 3 memorization strategies. So 6 times 3 is 18. So the degrees of freedom total is 18 minus 1, which is 17. Degrees of freedom within treatments, that is just simply adding up the degrees of freedom within each of the treatment groups. So there's 3 of them. And in each group, we have 6 people. So in each of the treatment groups, we have 6 people. So our degrees of freedom in each treatment is 6 minus 1 is 5. So we can just add 5 plus 5 plus 5 is 15. Or we could say that the degrees of freedom is 5 and we have 3 groups. So 5 times 3 is 15. Our degrees of freedom between treatments is going to be the same as what we've always had because we're just using 3 levels. So we have 3 levels of the memorization strategies. So the degrees of freedom between treatments is 3 minus 1 is 2. Then we take the degrees of freedom between subjects. That's just simply small n minus 1. What's small n? Well, how many people are in our study? There's 6 people. So 6 minus 1 is 5. And the final thing is for the degrees of freedom is we have to find the error. That's always the final thing. So error is always going to be within minus between subjects. So degrees of freedom within minus degrees of freedom between. So within is 15, between is 5. So 15 minus 5 is 10. We can also do this saying k minus 1 times n minus 1. That's a small n. So k is 3 and small n is 6. We have 6 people. So 3 minus 1 is 2. 6 minus 1 is 5. So 2 times 5 is 10. So either approach, you'll get the same number. And I'm going to sort of blow this up a little bit here. And then remember that for our f-test, all we need is the mean squares between treatments. That's the same for one-way and repeated measures ANOVA. But we also need the mean squares error. So the mean squares error is on the bottom of the f-test. So we need to get those two mean squares. To get mean squares, we always take sum of squares divided by degrees of freedom. It's an average, mean squares, average variance. So take the sum divided by the number, which is degrees of freedom in this case. So sum of squares between treatments divided by degrees of freedom between treatments, 22.39 is the mean squares between treatments. We do the same thing for mean squares error, as we take the sum of squares error divided by degrees of freedom error. We just simply plug these things in, and our mean square error is 1.657. So now we have the mean squares between treatments, the mean squares error. We can divide those two to find the F. And we get an F of 13.51. We go to the table to find our critical value, remembering that our degrees of freedom between treatments is 2. Our degrees of freedom error is 10. So we go to 2 in the column of the table. We go to 10 in the row. And our critical F is 4.10. And we know that 13.51 is greater than 4.10. Therefore, we reject the HO. So there seems to be an effect of memorization strategy. We do our effect size, partial eta square. You can use either formula. I'm suggesting this formula because you do have a repeat of numbers, and it makes it easier. So sum of squares between treatments divided by sum of squares between treatments plus sum of squares error. So order of operations, you have to add these two things on the bottom first, and you get 61.35. Then you divide the sum of squares between treatments, 44.78, by 61.35, and the partial eta square is 0.73, so that's a large effect. So 73% of the variance in the test scores, the memorization test scores, seems to be directly related to the memorization technique. So now we've calculated everything. Now we're just going to go down and remember to do your table 1 for descriptive statistics with the mean and standard deviation between the two. And we can kind of see, since it was a significant effect, we can kind of look here, and it looks like maybe rhymes greater than chunking, and that's greater than repetition. So that kind of seems to be what's going on. And then you have your ANOVA summary table. So again, don't need to include total, especially if it's going to confuse you. These parts are the same as the one-way ANOVA. This is still the old same thing. And then the new stuff is that we are going to take the within, subtract the between subjects to get the error. So that's true for the sum of squares. Within minus between subjects equals error. And it's true also for degrees of freedom. Within minus between subjects equals error. And then we need two mean squares to find out our F. So we do the between treatments. We take sum of squares divided by degrees of freedom to get the mean squares. And we do it for error because that's on the bottom of the F formula. So we take the sum of squares divided by degrees of freedom to get the average mean square for error. To figure out the F, you take the mean square between treatments, divide it by the mean square error. And this is the F that we calculated. And we rejected the HO at the 0.05 level, so we just put a little star there to let people know. Our write-up is exactly the same format as we've been doing all along here. And so we want to make reference to Table 1 and Table 2. And then I didn't do it in the last one. I'm not going to be a big stickler on this, but the official way of doing it is saying using a repeated measure sample ANOVA. Then we have the sentence about whether the IV and DV are related. So the IV memorization strategy had a significant effect on the DV, which is test scores. So the IV and the DV were related. So it seems, since we have an IV here, we can say that memorization strategy affected test scores, the DV. We include our stat information. So F, 2 is degrees of freedom between treatments. 10 is degrees of freedom error. That's what we used for our looking up of the critical value on the table. 13.51 is the F that we calculated, and remember that we set the alpha at 0.05, and so we rejected the HO, so the probability of a type 1 error is less than 5%. So that means it's a significant finding. You can put the effect size here or at the end, it doesn't really matter. It's large, partial eta squared, 0.73. So it's significant, so we can do post-hocs, but we didn't do it. We aren't doing it by hand, so we say, very sorry, we did not do it by hand. However, if we look at the table 1, it looks like rhyme is the highest than the other two. And also chunking looks like it was better than repetition. So I'm just going to show you that again. Rhyme was the highest, right? The higher one. So it's better than these two other strategies. But then if we look further, it looks like chunking, of the other two, chunking was better than repetition. So we just say those things simply in words. And I think that's it for this video, and I hope that this was helpful. And I know that these problems are long, but things get better after this unit. We get shorter problems. So I will talk to you later.